Okay, this is OCR A-Level Physics 2019 Paper 1 Modelling Physics. Multiple choice first, nice and easy. Number 1, which order of prefixes is correct? Okay, so A, we have micro, milli, centi, and kilo. Yes, that's correct, so the answer has to be A. Easy start. 2, paper cone is held above the ground, falls vertically, reaches terminal velocity before it hits the ground. Which statement correctly describes the resultant force on the falling cone before it reaches terminal velocity? So we know that weight is staying the same, but before it's falling, the drag has to be smaller than the weight. Once it reaches terminal velocity, it matches the weight. So once it reaches terminal velocity, it's like that. So the resultant force is downwards to begin with, of course, but it is decreasing until it reaches 0. So therefore we're going to say it's decreasing and downwards. It's B. 3, cylindrical glass rod has a length that with that uncertainty, diameter that with that uncertainty. What's the percentage uncertainty in the calculated volume? Okay, so volume is equal to area times length. So therefore we're going to add up the percentage uncertainties of both. So therefore, percentage uncertainty in L is equal to 0.1 divided by 20 times 100. That is 0.5%. Percentage uncertainty in A is equal to 2 times the percentage uncertainty in the diameter. So that's equal to 2 lots of 0.01 divided by 5 times 100. Or in other words, 1 divided by 5 times 2. So that's 2/5. And so that gives us 0.4%. So therefore, we have our two uncertainties. Add those together, we end up with 0.9%. So the answer is D. That is a lot of work for a 1 marker. 4, SHM oscillator has a maximum speed of that, amplitude of that. What's its angular frequency? So we have V max, I'm just dropping the max, we have A. We're looking for omega. The equation is V is equal to omega A. Therefore, omega is equal to V divided by A. So it's 24 divided by, careful, it's in centimeters. That gives us 429. So the answer is D. 5, a car is dripping oil at a steady rate on a straight road. Okay, which section of the road shows the car traveling at a constant speed? Are you serious? That's ridiculous. It has to be C because they're equal distances apart. Wow. I think that's possibly the easiest multiple choice question I've ever seen. Number 6, the Earth is surrounded by a gravitational field, blah, blah, blah. What is true about the field lines near the surface of the Earth? Okay, that's a bit mean. So if we're talking about near the Earth, then we're looking at things very closely. So we're not looking at this. So forget about that. We're looking at this, but that's a bit mean because, you know, near, bit subjective, whatever. They are parallel. Yes. They show the direction of force on a small mass. They always do. Yes. They're equally spaced. Yes. So therefore, it's all 3 of them. D, bob is oscillating in a vacuum. Maximum height of the bob. Oh, we have a height. Ugh. What do I always say? If you see a height, then you know it's going to be all about energy. It doesn't matter what this is. If we have a height, we can find out the speed. So all we do is say that kinetic energy at half mv squared is equal to gp, that's mgh. M's cancel, therefore speed is equal to square root of 2gh. So that's square root of 2 times 9.8 times, what's the difference? 0.2 meters, methinks. And that gives us like 1.98, so therefore the answer is going to be A. 8, an object is falling. Weight of the object is that, so that's mg. Do we even care about that? Don't know. Oh, no, we don't. Okay, let's draw a diagram. Absolutely. So we have weight pulling down. We have wind fighting horizontal force. Horizontal force, okay. So that way. And we have, oh, that's it. Okay, fine, because there's no air resistance. What is the value of F? Oh, we're given the resultant force. Okay, so resultant force is there. So that's 5.8 newtons. And we are given the weight of 4.5 newtons. So therefore, we're just going to use Pythagoras. I'm just going to call that R. We know that R squared is equal to the weight squared plus that force squared. Therefore, F is going to be equal to the square root of R squared minus the weight squared. So that's equal to square root of 5.8 squared. Take away 4.5 squared. And that gives us 3.66. So therefore the answer is B. 9, solid melts, blah, blah, blah. Which of the following pairs of quantities remains the same as the substance melts, so it remains the same. A, kinetic energy of molecules and internal energy of the molecules. No. Kinetic energy, yes, but internal energy, no, because remember, internal energy is kinetic energy plus potential energy, and we know the potential energy is changing when something melts or whatever, the opposite. Okay, potential energy, no, definitely not staying the same, so that's not true. Kinetic energy of the molecules and temperature of the substance. Yes, we know that temperature stays the same when you have a change in state. 10, which of the following shows the correct unit for pressure? Pressure is equal to force divided by area. Force is equal to mass times acceleration, and that's divided by area. So the units of that is equal to kilogram meters per second squared divided by meters squared. Therefore, one of these m's cancels. So therefore, that gives us kilograms, meters to the -1, seconds to the -2. So the answer is C. 11, solar system. We have 2 points. The distance from the center of the sun is r, which quantity y is represented on the vertical axis. Okay, so these are not proportional. This is not a straight line graph, because we know that, well, there'd be a point there. It's not a straight line graph, so it's that there. So we can say that y is going to be proportional to r to the power of something, but it's not going to be 1. We know that y is not going to be directly proportional to r. Okay, let's have a look at A then. Speed of a planet. Well, if we do mv squared over r is equal to gmm over r squared, centripetal force is equal to gravitational force. One of those cancels, one of those cancels. Therefore, v, ultimately we can see, crossing all of these out, v squared is proportional to 1 over r. So it's not that. B, the period of a planet. Well, from Kepler's law, we know that t squared is proportional to r cubed. So therefore, t is proportional to r to the power of 3 over 2. So yes, it could be that, because this is greater than 1. So therefore, we'd expect this curve upwards. So it could be that. So I'm going to say it is. Let's just check the other ones. Gravitational potential, V, we know is inversely proportional to r, so it can't be that. And field strength, G, is inversely proportional to r squared, so it can't be that. So yes, B is the only one where it's proportional to r to the power of something greater than 1, so we end up with that curve upwards. If it was a 1 over something, we have this shape here instead. I'm sure you recognize that from like your inverse square law graphs, that kind of thing. 12, graph showing the variation of stress with strain, blah, blah, blah. What is the Young modulus of the steel? Well, it's only the linear portion of the graph that we're concerned with, so therefore we're going to say that that is 80, 160, so that's 120. This is 0.1. So therefore, we know E is equal to stress over strain. So we're going to say that that's 120, but that's megapascals, times 10 to the 6, divided by 0.1%. Right, okay, so we've got to figure out what that is first. 0.1%, but we need it in the decimals, so we know that's going to be 0.001. It's 1,000th, isn't it? So we can say 1 times 10 to the -3. So therefore, I can already see that it is going to be 1.2 times 10 to the something. But if we take the -3 onto the top, we end up with times 10 to the 9. So that is 1.2 times 10 to the 11 pascals. So the answer is D. 13, which column shows the correct sequence for the evolution of the universe, blah, blah, blah. Oh, I don't know. It's all guesswork. I can't stand these questions. Okay, I guess it starts with universe starts to expand, so it can't be C or D. And next, well, we know that hadrons are made from quarks, so therefore it can't skip straight to hadrons, so therefore the answer has to be A, apparently. 14, some stars will turn into white dwarfs, blah, blah, blah. We have a mass of the sun. Is that which of the following cannot be the mass of a white dwarf? This is one of those very niche bits of knowledge that you either know because you've read up on the stuff or you don't. It's something I don't really have on the top of my head. But whatever, white dwarfs are usually around, the mass is around 0.15 times to 1.2 times mass of the sun. So therefore, A can be possible, same as the sun, that's possible as well. I mean, it's a bit heavy actually, C is, but the point is that it's the biggest one that isn't going to be possible. It's going to be least possible. 15, astronomer analyzes light. One of the spectral lines can be observed as a wavelength that. Same spectral line is that when measured in the laboratory. What's the speed of this galaxy? Well, we know that recessional speed is equal to change in the wavelength divided by the wavelength times the speed of light. So that is 20 nanometers. We don't need to change it into meters because it's just relative, divided by the original 590. That's the rest wavelength times the speed of light. And that gives us 1.0 times 10 to the 7. So the answer is B. Okay, longer questions. What's meant by UTS of a material? It's the maximum stress a material can withstand before breaking. Fairly easy, but it does bug me that it's not called ultimate tensile stress or just maximum tensile stress, whatever. Okay, footbridge is supported by a number of these metal cables. They have a diameter of that. So we're probably going to find out the area from that. Let's do that right now, actually. Area is equal to pi d squared over 4. So that's pi times 4.2 times 10 to the minus 3 squared divided by 4. And that gives us a cross-sectional area of 1.39 times 10 to the minus 5 meters squared. Okay, probably going to come in handy later. So we're looking at force against extension. Cable breaks at that much force. Describe how a suitable measuring device may have been used to demonstrate that the cable had uniform cross-section. We can use a vernier caliper or a micrometer, and of course whenever we do that we measure at multiple points along the cable. Part 2, state any value of F when the cable behaves elastically. Okay, so when it's elastically we're talking about this bit here. So I don't know, we can just go for 1 kilonewton, easy. And then plastically we've gone past this bit, we're into the plastic region over here. Bear in mind that the elastic limit can still be past the limit of proportionality. So there's the limit of proportionality, but the elastic limit is usually past that. So let's go a little bit further, shall we? Let's go for, I don't know. Let's go for that point there. So let's call that 2.1. Find the force constant K of the cable. So just take a nice point. Let's just take this point here. So we have 1.5 kilonewtons and 3 millimeters. And hey, I mean, they've given us the units, haven't they? So even if you can't remember the equation, it's all there. So 1.5 times 10 to the 3 divided by 3 times 10 to the minus 3. And that's going to give us, even without using a calculator there, just 0.5 times 10 to the 6, or in other words, 5 times 10 to the 5 newtons per meter. Fine, probably should go to 2 sig figs there, seeing that the graph was to 2 sig figs. Determine the breaking stress of the cable. Here we go, told you. Stress is equal to force divided by area. The maximum force, looking from the graph, is 2.2 kilonewtons. So I'm just going to say 2,200 divided by, what did we say that was? 1.39 times 10 to the minus 5. And that gives us 1.58 times 10 to the 8 pascals. But seeing that the graph is to 2 sig figs, that means that this number is to 2 sig figs. So we're just going to call that 1.6 times 10 to the 8. Do explain why the work done is greater in the plastic bit than the elastic bit. Same extension, but area under graph is greater for 3 to 4 millimeters. And second mark, bit cheeky if you ask me. They're expecting you to say something like work done is equal to force times distance. And so therefore, for 3 to 4 millimeters, average force is greater, because of course it's not going up like that. It's just curving over like that. So therefore the force is going to be greater, the average force. Not that nice, that question. 17, student uses a motion sensor connected to a laptop, blah, blah, blah. We have a mass. So that's just 0.012 kilograms. Once again, it reaches terminal velocity before it reaches the ground. No upthrust. And we have a graph. Fine. Draw a tangent to the curve at t equals 0.25 seconds and determine the acceleration. So 0.25 is here. We're going to get a ruler. I'm not going to get a ruler though. You should. Oh, that's not bad though. Maybe a tad on the low side. I don't know. That's pretty darn perfect. Don't forget that you have to make a fairly big triangle. You don't want to go for a small triangle, otherwise you won't be accurate. And we're talking about difference in v divided by difference in time, and that should give you about 1.3 meters per second squared. Oh, it's a hollow ball. Okay, it's very slow. Very, very slow. Whatever. Calculate the resultant force of the ball acting at that time. So F is equal to mass times acceleration. Easy. So that's 0.012 times our acceleration, whatever you got. And that gives us 0.016 newtons. Use your answer to calculate the drag on the ball at time t equals 0.25. Oh, of course, drag is not the same thing as upthrust, right? So why did they even mention upthrust? It's a bit weird, isn't it? Whatever. So, draw a diagram. We have here weight pulling downwards. We have drag pulling upwards. And we know that adding those together, we are going to have a resultant force just pulling down. So therefore, I'm going to say that F is equal to weight minus the drag. Therefore, drag is equal to the weight minus the resultant force. So there's going to be mg take away a resultant force of 0.016. So that's 0.012 times 9.8. I mean, we could do this all in one go, really. We could just times it by 1.3 instead. Doesn't really make a difference which way around you do it. And that gives us 0.102 newtons. But we're going to go to 2 sig figs, so 0.10. Student now adds a small amount of sand inside the ball and reach terminal velocity. Describe how the force is acting on the sand-filled ball at v 0.5 meters per second compared with the forces acting on the hollow ball at this speed. So at v 0.5 seconds, it's still accelerating, right? So bigger mass is equal to bigger weight. As resultant force, F is equal to the weight minus the drag. Oh, we know the drag is constant because it's the same shape or area. So because force is equal to W minus D, that means that force will be bigger. Explain why the terminal velocity of the sand will be greater than the terminal velocity of the hollow ball. It's all because as weight is bigger, larger drag force needed to balance. Therefore, faster speed needed as larger V results in a larger drag force. There we go. Fairly easy. 18, bit of SHM it looks like. Okay, so we're in a vacuum, blah, blah, blah. And we have it at t equals 0. Fine. So we have a time. And we have an acceleration. And we have a displacement. Okay. Yes, I know the letters are already there. Whatever. Use a defining equation for simple harmonic motion to show the natural frequency F of the spring system is about 1.4 hertz. So we have an acceleration and we have x. And so if we have an acceleration, of course, we write down straight away a is equal to minus, don't really care about the minus, omega squared x. And we might need the time later on, but not yet. So a is equal to 2 pi f all squared times x. Rearranging this, a over x is equal to 2 pi f square root that. So f is equal to the square root of a over x divided by 2 pi. So numbers wise, that's square root of 3.6 divided by, what's the displacement? 0.046. Divide that by 2 pi. And that gives us 1.40, but we're going to put that to 2 sig figs. 1.4 hertz. Calculate A, the amplitude. So let's have a think. We are looking for an amplitude. What do we have? We have an x, we have acceleration, and we have a time. What equation has amplitude in? Well, the speed equation does, but we're not dealing with that, maximum speed that is. But we know that the initial equation for SHM is the displacement at any time is equal to the amplitude times sine or cos. Ooh, are we going to use sine or cos? Let's have a look actually. So look at this. At time 0, it's not at equilibrium. So we use sine if the ball is at equilibrium to begin with, but if it's at amplitude, then we're going to use cos. So therefore, amplitude is equal to x over cos omega t. So that's going to be x over cos 2 pi ft. So what do we say that was? 0.046 divided by cos of 2 pi. Don't forget you must be in radians whenever you have any cos or sine with pi's in. When you're doing SHM, you're usually in radian mode. Times 1.4 times, what was the time? 6.5. All right, big equation. I recommend doing the bottom bit first. Don't forget to be in radians, like I said. That's effectively 0.046 divided by 0.809. And that gives us 0.057 meters. B, mass spring system now oscillates in air. Different types of energy involved in the oscillation of the mass spring system. Describe the energy changes that will take place as the mass moves from the lowest point in its motion through the equilibrium position to the highest point in its motion. Okay, so we know that when it's at the bottom, we know that we have minimum GPE, but we have max elastic potential energy. So therefore we can say that as it rises, GPE increases as E equals mgh, fine. But elastic, or we can say strain energy in spring, decreases as E is equal to half kx squared. But we know that also ball does work against air resistance. And last but not least, we also know that when spring changes shape, its temperature is raised. Therefore, the elastic potential energy gets turned into GPE plus work done against air resistance plus heat produced in the spring. Okay, we have it attached to a mechanical vibrator. It can oscillate with variable frequency. Okay, so the vibrator frequency is varied from that. So that we know that the resonant or natural frequency is 1.4 hertz. So being asked to show the variation with vibrator frequency of the amplitude of the mass. Right, we know that we have the max amplitude when the driving frequency is the same as the resonant or natural frequency. So there's 1.5, so 1.4 is 1, 2, 3, 4. Let's say that it's there. So we know we're going to have a maximum amplitude. So of course we're going to have a maximum amplitude at this frequency. So let's just put a cross up there. It's not going to go down to 0, of course. It is going to oscillate a little bit, but we can do something like this. There we go. Light disc is now attached to increase the damping. Vibrator frequency is again varied. Sketch a second graph to show the new variation of the amplitude. Label this graph D. So we end up with the graph being shifted slightly to the left, and also because of the damping we have a lower amplitude as well. So something like this. Explain why the phenomenon demonstrated can cause problems for engineers when designing suspended footbridges. So we saw this happen with the Millennium Bridge in London. Footsteps act as driving force. If frequency is similar to the natural frequency, resonance can occur. What does that mean? Amplitude increases and can cause bridge to break. 19 cars traveling at that speed. Okay, this is probably Suvat, isn't it? Okay, so we have a distance, we have a time. Oh no, that's our reaction time, isn't it? And we have our speed as well. I should really call that U. Calculating the magnitude of the deceleration of the car when the brakes are applied. So the stopping distance is 38 meters. So don't forget that stopping distance is equal to, well, we can call that thinking distance plus braking distance. Okay, we know that thinking distance is just the initial speed times the time. Braking distance, we know that's going to be to do with the deceleration. So let's find out the braking distance first. So braking distance is equal to the stopping distance, take away the thinking distance. So that's equal to 38 meters, take away 18 times 0.5. So in other words, take away 9. So that is 29 meters. Okay, so we have 29 meters. So now we can use Suvat for the braking distance. We're looking for the acceleration because we're looking, oh, that's what we're looking for. We're not even looking for the force. V we know is 0 because it's coming to a standstill. U is 18 and S is 29. So therefore we can use V squared equals U squared plus 2AS. V squared disappears. Yes, we can say basically V squared is equal to 2AS. Yes, there's a minus in there, but it doesn't matter. We're just going to end up with a minus instead of plus at the end. Therefore, acceleration is equal to U squared divided by 2 lots of the distance. So that's 18 squared divided by 2 times 29. And that gives us 5.59 meters per second squared. So we're going to say that's 5.6 because our data was given to 2 sig figs. Okay, B, student rolls a marble, different speeds to model the braking of a car. So investigating X before the marble stops. It depends on this initial speed V. Speed and distance X are related by the equation that. So energy equals energy. Fine, work done, whatever. And describe how an experiment can be conducted in the laboratory to investigate the relationship between V and X. Explain how the data can be used to determine F. Oh, right. Fine. I hate these kind of code. This is so wishy-washy. But we can say we can use a ruler to obtain distance x. We can use a balance to obtain the mass, the marble. We can use a light gate to obtain velocity. They really should have called it U, right? But whatever. We can obtain repeat readings for the same V. And this can be achieved by using track. We should say angle track. Marble can be dropped from the same height to get the same velocity. What we can do is plot a graph of v squared against x. If straight line through origin, v squared is proportional to x. We want to find the frictional force. We saw that half mv squared is equal to fx. Therefore, rearranging it, we see that v squared divided by x gives us f divided by a half. So that's just 2 divided by the mass. That's equal to the gradient. Therefore, the force is equal to the gradient. Therefore, force is equal to the gradient times the mass divided by 2. Ugh, there we go, that'll do. 20, bicycle manufacturer, initial speed u, we have a time, force against time, fine. Force against time, we know this is going to be to do with impulse, isn't it? FT graph, that's literally the only thing you can find. Use Newton's second law of motion to explain the physical quantity represented by the area under the graph. Force is equal to mass times acceleration, which is equal to mass times change in velocity over change in time. Or in other words, change in mass times velocity divided by time, which is the same as impulse or change in momentum. Total mass of cyclist, and that is 71 kilograms. So we're being asked to find initial speed u. So the impulse is going to be 900 times 2. So the impulse is 900 times 2 divided by 2 because it's a triangle. So therefore it's 900 kilogram meters per second or Newton seconds, whichever unit takes your fancy. This is equal to m times u. Therefore, u is equal to the impulse divided by the mass. So that's 900 divided by 71. And that gives us 12.7 meters per second. We're going to get a 2 sig figs. That's 13. Complete the graph to show the variation of speed. So, a little bit confusing this one. Could catch you out, but let's have a think. We know that at the beginning, we have a high force. And then by the end we have 0 force. So we said that it starts at u, didn't we? But we're told that it stops at that. So we know we're going to end up here. But is it going to be a straight line going down? No, it's not. Because the force is changing, that means the acceleration is changing. So changing acceleration means that the gradient is going to be changing. It can't be a constant gradient. So therefore it's going to get down like this. 21 looks like changing of states, blah, blah, blah. So use a kinetic theory to describe the solid phase and the liquid phase in terms of motion arrangements of the molecules. Oh, come on, really? Do we have to do this? So solid and liquid, particles close together, particles close together. Now, what's interesting is that the mark scheme says that they're slightly further apart for the liquid. That would imply that you could squash water. I'm not so sure that they're right about that one. This is such a year 9 question, isn't it? Look, it's all in the mark scheme. You guys know it already, don't you? But then we are being asked to describe what's happening in these regions, and the temperature is going up. So we can say as temperature increases, particles gain Ke, same for the liquid. And you can say other things like amplitude is increasing, they're moving faster, blah, blah, blah. There we go, that's plenty for 4 marks. Okay, use the graph to explain how the SHC of the liquid compares with the SHC of the solid. So let's have a look here. We have a higher gradient here. That means it's easier to raise the temperature. Therefore, that means that it has a lower SHC, because remember that SHC has the units joules per kilogram per degree Celsius or per Kelvin, whatever. So in other words, if you have a low SHC, you need fewer joules to raise the temperature. So that's why lower SHC materials are easier to raise the temperature of. So we can say lower SHC as temperature of material increases more quickly. Quicker? Yeah, whatever. State what is meant by internal energy. This should be ready to go. Is equal to the sum of kinetic energy and potential energy of all particles in a substance. You should write that out in full. Okay, beyond E, it behaves as an ideal gas. the mass of a gas molecule is that. Marvelous, so that it is m in our equations. Calculate the root mean square speed, so we're looking for C, RMS, or C, whatever. And we have a temperature of that. We need to change that into Kelvin, first of all. So that is 523 Kelvin. So we need an equation that has T, or theta, I prefer T, M and C in. We know that the kinetic energy of molecules is given by 3/2 kT. So in other words, half mc squared, I'm just dropping the RMS, is equal to 3/2 kT. Halves disappear. Therefore, C is equal to 3 kT over the mass, all square root. So popping that all in, that gives us 672 meters per second, but 2 sig figs, going to go 670. Could have tidied up powers of 10 there by doing that, something like that. Maybe a wee shortcut there. Calculate the internal energy of 1.3 moles of the gas at 250 degrees C. Calculate the internal energy of 1.3 moles of the gas at that temperature. So we have the energy of one molecule. So total energy is equal to number of molecules times the energy of one of these. So therefore that's going to be number of moles times Avogadro's constant times the energy of one of the molecules. So in other words, n times Avogadro's constant times half mc squared, but of course we can just replace that with 3/2 kT. So that's 1.3 times Avogadro's times 3/2 times Boltzmann's. We can just cancel out those powers there, that's useful. And we end up with 8,473 joules, but we're going to do that to 2 sig figs, that's 8,500 joules. 22, screw with a screwdriver, blah, blah, blah. We have the width and equal forces. Okay, so we look like we have a couple here. Calculate the magnitude of the torque of the couple produced by the forces at each end of the screwdriver blade. So we know that that's in the middle there. There's our radius, but if we're just finding the torque of the couple, then we just need to do one of the forces times the distance between them. Doesn't matter whether you do both forces times the radius, add it together, whatever. And that gives us 1.75 or 1.8 Newton meters. Wooden sign, blah, blah, blah. Okay, this is all moments, it looks like. We're being asked to calculate the maximum mass of the wooden sign. Fair enough. Okay, so maybe this isn't that complicated. All we have to do is take moments around this point here. So we can take R out of the equation. We have F pulling clockwise, we have 31 pulling anti-clockwise, so we can say that their moments are equal and opposite. So therefore we can say that 31 times 0.03, that's force times distance for the screw inside the wall, is equal to 0.007 times this force, the weight pulling downwards. So therefore, just rearranging this, that gives us 133 newtons, but we know that's equal to mg. We're looking for m, therefore we're going to divide that by g by 9.8. And we get to 2 sig figs, 14 kilograms. Okay, 23. In 2017, an ultra cool star, TRAPPIST-1, was discovered with at least 5 of its own orbiting planets. Well, isn't it super duper special? Okay, possibility of finding life. Oh, shut up. Whatever. We have the luminosity, temperatures, blah, blah, blah. Temperature T, distance D, blah, blah, blah. The average temperature of the Earth is about that. Explain how life may be possible on some of the planets orbiting TRAPPIST-1. Oh, yes, as if temperature is the one thing that you need. Goodness gracious me. So, first thing we can say is that TRAPPIST-1 is cooler than the Sun, but the planets are closer. Therefore, temps may be similar to the Earth. And what for? Even if... no, I'm not getting into it. Let's just get this over with. To be fair, the mark scheme does say for life to exist, temperature isn't the only factor. There's a million other things. So we're told that the temperature is given by that equation. So let's find out what this constant is for the Earth then, shall we? So temperature to the power of 4. We're talking about the temperature of the planet. So there's 290 to the power of 4 times the distance that we are from the Sun. So that's 1.5 times 10 to the 11 squared. squared divided by the luminosity, which is 3.8 times 10 to the 26. And that gives us 4.2 times 10 to the 5. So there we go. So therefore, we can now use this constant to find out what the temperature is for the other planets. Actually, you probably realize that we could have just equated the two together, but you know, it's complicated, so let's do it one step at a time. So I'm just going to call this constant K. So therefore, temperature to the power of 4 for the other planets is going to be this constant times the luminosity divided by the distance squared. So therefore, fourth root will give us the temperature. So it's the fourth root of the constant times the luminosity, which is 2 times 10 to the 23, divided by the distance squared. We're looking sort of for an average here, aren't we? So let's go for something in the middle, like, we can just go for 5, can't we? 5 times 10 to the 9, and that is squared. And it gives us 240 Kelvin. Now the mark scheme says you should do it for the innermost and outermost planets, so both of these. And if you do that, you'll find they go from 180 Kelvin to 430 Kelvin. So we can say, therefore, probably a planet between with similar temperature to the Earth. Okay, so we dealt with the temperature side of things, but now we need to deal with the radius of this star. So radius is all to do with luminosity. So luminosity is equal to 4 pi r squared times Stefan's constant times temperature to the 4. A couple of ways we can do this. We can actually find the radius by doing the calculation, or we can just say that luminosity is proportional to r squared t to the 4. Therefore, r squared is proportional to L over t to the 4. So this value for the sun is about 3 times 10 to the 11, but for TRAPPIST-1 it is 2 times 10 to the 23 divided by 2500 to the power of 4. That gives us 5 times 10 to the 9. Therefore, R is smaller for TRAPPIST-1. Yes, you could just rearrange this whole equation to find the radius and compare the two as well. But this is a shorter way. I've wasted enough time in this question already. B, Kepler's third law can be applied to a satellite, blah, blah, blah. Complete the equations for Kepler's third law. Below, you do not need to define any of the terms. Well, we know that m omega squared r, because when it comes to Kepler's law, we're talking about time periods, so we need the angular speed version of the centripetal force equation, gm over r squared. R goes to the other side, so we end up with that. We know this is 2 pi over t all squared. Because g, we can get rid of an m as well, can't we, of course? And this, of course, is 4 pi squared over t squared. So flipping everything on its head, we end up with t squared over 4 pi squared is equal to r cubed over gm. If we put this over here, we end up with 4 pi squared there. So therefore that's our constant. So we're looking at t squared there and r cubed there. Mass of the Earth is that. Calculate the radius of the circular path of a satellite in a geostationary orbit. Okay, so we know. Okay, so let's find out what the time is first. We're talking about a satellite going around the Earth, so geostationary orbit. So therefore the time period is 1 day. So 24 hours times 3,600 gives us 86,400 seconds. So now all we have to do is pop the numbers in. So that's going to be G 6.67 times 10 to the 11 times 6 times 10 to the 24 times 86,400 squared. Divide that by 4 pi squared, and then we just need to cube root all of that. And that gives us two sig figs 4.2 times 10 to the 7 meters. 24, Proxima Centauri is the closest star to Earth. We have the background stars. Okay, 2 centimeters equals 1 arc second, right? The parallax angle for Proxima Centauri can be determined from the diagram using the scale provided. So the parallax angle P for Proxima Centauri is about 0.8 arc seconds. Okay, so this distance here, if we measure that, you end up with 3.1 centimeters. So therefore, 3.1 centimeters divided by 2 centimeters per arc second gives us 0.78 arc seconds. Use your answer to calculate the distance d for Proxima Centauri from the Earth in light years. So distance is equal to 1 over the angle in arc seconds. So it's 1 divided by 0.8. So that gives us 1.3 parsecs. Times that by 3.26. And that gives you 4.2 light years. Mark scheme has used 0.8 from the previous question, so you end up with 4.1 if you do that. B, the galaxies in the universe distributed uniformly through space. They're not actually, if you look into it. Concentric spheres, it's really weird. Anyway, in this model, the separation between two neighboring galaxies is that, and each galaxy occupies a cube of space of that. Okay, there are on average 10 to the 11 stars in each galaxy, and the mass of the average star is about that many kilograms. Okay, estimate the gravitational force between two neighboring galaxies. Okay, so force is going to be equal to gm over r squared. But if we're talking about the same mass of each galaxy, then we're just going to say m squared. Okay, so what is the mass of one galaxy though? Well, we know that it's going to be the average star, so 2 times 10 to the 30 times 10 to the 11. So therefore that is 2 times 10 to the 41. So therefore F is going to be G times 2 times 10 to the 41 squared divided by, okay, what was the separation? 1.4 times 10 to the 23. And that is squared as well. And that gives you 1.36 times 10 to the 26 newtons, or 26 figures 1.4 times 10 to the 26 newtons. So the mean density of the universe is about that. So density of the universe is going to be the same as the density of the cube. Therefore, that's mass divided by volume. So that's going to be our mass that we just figured out, 2 times 10 to the 41 kilograms divided by the size of the box. There's our volume there, 2.7 times 10 to the 69. And it gives us a very small density of 7.4 times 10 to the minus 29 kilograms per meter cubed. Suggest why the actual mean density of the universe is different from the value calculated in that. What a weird question to end on. Average mass of star. Could be wrong, as could observed differences. Basically, it's all guesswork. And so what's even the point? So I hope you found that helpful anyway. If you did, please leave a like. And if you want to see the other papers, then click on the card and it'll take you to the playlist. See you next time.